Dot tally with BPE, a two-dimensional tally notation with layer-dependent word bonding. One letter, one square, and dots spread across a grid, black and white only, benchmarked directly against zip. 14 dots, spread in 2D equals letter N. Aaron Cattell. A dictionary and recipe compression architecture rendered as spread dot counts, proven lossless under simulated real-world degradation, and benchmarked against production compressors. Abstract. We present dot tally, a black and white positional letter notation, in which the nth letter of the alphabet is drawn as n discrete dots spread across a fixed two-dimensional grid within a small square. Words are stacks of such squares, a shared dictionary of unique word tiles, detected by direct pixel comparison, plus a per-document recipe of pointers avoids redrawing any repeated word, saving 83.3% over an underduplicated rendering on our test corpus. We show experimentally that the two-dimensional spread is not a stylistic choice, but a load-bearing design decision, a naive one-dimensional variant, tally lines packed into a single row, fails completely the 0 of 26 letters, under simulated real-world degradation, while dot tally survives it completely 26/26. Separating the notation's dictionary and recipe architecture from its rendering, we further show the architecture alone beats zip by 37% when both are given an identical shared vocabulary advantage, 74 vs. 118 bytes, a result independent of dots, squares, or any visual choice, with the subsequent cost of rendering that architecture as a legible image quantified separately and honestly. Section 1 The Notation. Definition 1.1 Dot tally square. Fix an alphabetical index n sigma, set membership symbol \1, 26 before each letter sigma. A letter is drawn as a square containing n sigma filled dots, placed at fixed positions on a 6-column reference grid filling the square, read left to right, top to bottom. No numerals, no color, and no line ever appears in the notation, only isolated black dots on white. A equals 1 dot, B equals 2 dots, C equals 3 dots, Z equals 26 dots. Figure 1. For dot tally squares. Dot count alone determines the letter. Position within the square carries no independent meaning beyond keeping dots separated. Cat. Dog. The. Rat. Figure 1b. For real, rendered dot tally word tiles, unmodified pixel output from the actual test pipeline, with their decoded text beneath each. Definition 1.2 Word and sentence. A word of length m is m squares stacked vertically, read top to bottom. A document is a dictionary of unique word tiles, rendered once each, plus a per-sentence recipe of pointers into that dictionary, identical in structure to the architecture used in the companion notation, differing only in how a single letter is drawn. Section 2 Why 2 dimensions, not 1. A tally count can be drawn two ways, as parallel lines packed into a single row, or as dots spread across a two-dimensional grid. We tested both under an identical degradation model, a mild Gaussian blur, sigma equals 1.1, followed by additive pixel noise, plus or minus 14 levels, simulating a photocopy, or a low-quality scan. Variant. Clean read. After blur plus noise. Tally lines, 1D, packed in a row. 26/26. 0/26. Dot tally, 2D, spread across a grid. 26/26. 26/26. Result 2.1 The mechanism of failure. Gaussian blur is an averaging operation. A mark averaged predominantly with itself, an isolated dot, or a solid color region, is perturbed only slightly. A mark averaged with closely spaced neighbors is not perturbed, it is merged. 26 parallel lines confined to one square necessarily sit only a few pixels apart, blur does not shift their count, it destroys it, collapsing every letter to the same unreadable smear regardless of its true value. Spreading the same 26 marks across 2 dimensions increases the minimum pairwise separation for a fixed square area from O1 n to O1 square root n, which was sufficient, at the tested square size, to keep every mark fully isolated under the same blur radius. 26 lines, 1D, blur merges neighbors smeared, unreadable 26 dots, 2D, blur stays isolated every dot still readable. Figure 2. Identical dot or line count, 26, identical square area, identical blur. Only the arrangement differs. Section 3 Benchmark. Test corpus, 20 sentences, 118 word occurrences, 19 unique words, 450 bytes plain text. Dot tally is applied at word granularity, with dictionary deduplication, as in definition 1.2, all figures below are measured directly, and full decode correctness across all 20 sentences was independently verified against the source text. With and without a shared dictionary. Rendering every word occurrence independently, with no reuse, costs 19,097 bytes for this corpus. Detecting repeated words by direct pixel comparison, the same tracing paper method used to verify sentence-level reuse elsewhere, and drawing each unique word once. Rendering bytes. No dictionary, every occurrence drawn fresh. 19,097. With dictionary, deduplicated by pixel comparison. 3,191. An 83.3% reduction from deduplication alone on the drawn artifact before any comparison to other software. The architecture beneath the drawing. The dictionary and recipe logic that produces this saving is independent of how a word is rendered, stripped of all drawing. It is a list of unique words plus a packed sequence of indices. This layer is measured on its own and compared fairly against XIP given the identical shared dictionary advantage. Method. Bytes. Notes. Plain text. 450. LZMA. 212. BZ2. 154. XIP, no dictionary. 145. XIP, with shared dictionary. 118. Fair baseline. Dot tally, dictionary plus recipe, standalone. 150. Dictionary not amortized. Dot tally, recipe only, dictionary amortized. 74. 0.63 times XIP, fair fight. Dot tally, drawn, deduplicated. 3,191. Full hand traceable image. Dot tally, drawn, no dictionary. 19,097. Every occurrence redrawn bytes for the abstract dictionary plus recipe layer, lower is better. Plain text 450 LZMA, 212 BZ, 154 XIP. No dict 145 XIP. With dict 118. Tally recipe 74. Tally's own architecture is 0.63 times XIP, even when XIP gets the same dictionary advantage. Figure 4. The dictionary and recipe layer beats every general-purpose compressor tested fairly. Rendering it as an image, Figure 3, is a separate, deliberate cost paid afterward for legibility. Result 3.2, architecture and rendering are separable. Dot tally's compression logic does not merely compete with XIP, it wins, fairly, by 37%, 74 versus 118 bytes, once both sides are given the identical shared vocabulary advantage. This result has nothing to do with dots, squares, or two-dimensional spread. It is a property of the dictionary and recipe architecture alone, and would hold identically under any rendering choice. The subsequent cost of drawing that architecture as a legible degradation-resistant image, roughly 43 times the recipe's own size, is the fully separate, honestly quantified price of visibility, not a symptom of an inefficient design. Timing and correctness. Metric. Value. Encode time, 19 unique word tiles. 40.94 milliseconds. Decode time, all 20 sentences, blind. 35.41 milliseconds. Decode correctness. 20/20th sentences exact. Deduplication correctness, repeat heavy corpus, tracing paper match. 10/10th sentences exact, 54.9% saved. Robustness under blur plus noise. 26/26 letters, versus 0, the 26 for the 1D Tally variant. Section 4 Conclusion. Tally's rendered form is not competitive with XZIP, BZ2, or LZMA on size, and was not designed to be. A black and white hand-traceable image will always cost more space than an optimized byte stream with no legibility constraint. Its dictionary and recipe architecture, however, is competitive. Stripped of rendering and given the same shared vocabulary advantage, it beats XZIP outright. What .tally demonstrates is that these two properties, an optimal compression architecture and a robust, verifiable, purely visual rendering of it, are genuinely separable and can both be true at once. The two-dimensional spread of Section 2 is a specific, provable fix for a specific, measured failure mode, not an aesthetic preference. A one-dimensional tally notation of identical information content fails completely under realistic degradation. .tally, differing only in the arrangement of identical marks, does not fail at all. Section 5. .tally with BPE. The dictionary and recipe architecture beneath .tally admits a further optimization, borrowed directly from byte pair encoding (BPE), the merge algorithm used by modern language model tokenizers. Repeatedly find the most frequent adjacent pair of tokens and merge it into a single new token, until a stopping criterion is reached. Definition 5.1 Word bonding. Given a corpus tokenized into words, let A, B be the most frequent adjacent word pair. Replace every occurrence of A, B with a single merged token A-or B, add it to the dictionary, and repeat for K merges. Each merge strictly cannot increase, and typically decreases, the total token count of the corpus. On the 20-sentence test corpus, 10 merges were learned, led by THE, OLD, at 10 occurrences, and SAT, ON, at 7. A merge count beyond roughly 10 begins to fold whole sentences into single tokens rather than capturing genuinely reusable bigrams. A dictionary tuned to erase one specific document would generalize poorly to the next one. So 10 merges was retained as the reported result rather than the lower values obtainable by overmerging. 5.1 The binary recipe, a real win. Applied to the pure dictionary and recipe layer, no rendering, no drawing, word bonding is unambiguously beneficial. Method. Bytes. Time per document. XZIP with shared dictionary. 118. 63.0 microseconds. Recipe, no word bonding. 74. 17.3 microseconds. Recipe, with word bonding, 10 merges. 46. 90.5 microseconds. Binary recipe size, bytes, lower is better. XZIP, with dict 118 recipe, no BPE 74 recipe, BPE, 10 merges. 46 word bonding. 61% smaller than FairXZIP, 38% smaller than the plain recipe, but 5.2 times slower to apply than the plain recipe. 10 merge passes per document. Figure 5. Word bonding at the binary layer. Smallest output of any method tested, at a real, honestly measured speed cost. 5.2 The drawn tile, a real loss. The identical merge rules, applied to the rendered notation rather than the abstract recipe, produce the opposite result. Rendering. Bytes. No word bonding, drawn, combined into one file. 433. With word bonding, 10 merges, drawn, combined. 636, plus 46.9%. Result 5.2, word bonding fragments reuse. A word's drawn cost is only cheap through reuse, one tile, pointed to many times. Merging breaks a heavily reused single word, the, which opens many sentences in the corpus, across several larger, individually rarer combined tiles, the-old, the-a cat, the-a dog, each redrawing these letters from scratch plus a blank word boundary square. The technique that helps the binary layer works directly against the mechanism that made the drawn layer efficient in the first place. Result 5.3, Layer-dependent optimality. Word bonding is not universally good or bad for this notation. It is good for exactly one of its two layers. All 20 sentences were independently verified to decode exactly, in both the merged and unmerged, and both the binary and drawn, configurations. The size results above are not an artifact of a broken comparison, but a genuine structural fact about where reuse value lives in each representation. Dot tally. A two-dimensional tally notation, benchmarked against XIP, BZ2, and LZMA, proven robust under simulated real-world degradation.